So please go and talk to them and ask your questions. Our next speaker is Zenna Tavares, who comes from the Massachusetts Institute of Technology. All right, the floor is yours. You appear to be on mute for now. Zenna, I don't know if you can hear me, but I don't think we can hear you, or at least I'm. Oh, I think it should be better.
Can you hear me now?
Yep, perfect.
Great. So, hi everyone. My name's Zenna Tavares. I'm a postdoc at MIT, and today I'm going to talk about some of the work we've been doing, trying to extend and generalize causal and counterfactual queries to probabilistic programs. So this is joint work with my collaborators Jimmy Koppel, Xing Zhan, my advisor Amanda Soledad-Lozano, and we're all at CSAL, although Xin is now in Peking University. So when I see an image like this, the thing that comes to mind is this person was very fortunate. And as a computer scientist, I want to understand how I've come to that conclusion and provide a computational account of this kind of reasoning. And so I'm preaching to the crowd here, but I think a large part of this problem can be understood in the context of probabilistic programs. So we can look at this image, we can infer the three-dimensional structure of the world, where the objects are, we can infer the plausible trajectories of this car driving and crashing, and these things require models of the world. But we can also ask counterfactual questions, right? So what would have happened had this barrier not been here? And all the, would they have survived or would they have been hurt? To take another example, there's many kind of causal questions which are coming to the forefront now given the current pandemic. One thing that I'm sure everybody's familiar with is this question of masks. So, does wearing a mask prevent the spread of the disease? If we had a different mask policy, could we have, prevented some number of infections or some number of deaths? And again, along this theme, a few weeks ago in the vice presidential debates, I noticed this counterfactual by Mike Pence. He says, if the swine flu had been as lethal as the coronavirus in 2009, when Joe Biden was vice president, we would have lost 2 million American lives. So I bring up these examples for a bunch of different reasons. So first, like I said before, counterfactuals require models of the world. Second, they're clearly important. They've been used in vice presidential debates. Third, often counterfactuals are used in service of something else. So in this case, we're trying to either to attribute blame to some other party or absolve responsibility. And finally, there's a sense in which counterfactual claims can be true or false. And I'll leave it up to you to decide whether you think this is a true or false counterfactual claim. So the structure of my talk will be basically three parts. First, I'll give a high-level overview of counterfactuals and what I'm calling counterfactual generative models. Second, I'll give a very high-level overview of how we're dealing with some of the problems in this language / library called Omega. And finally, I'll give some open problems and future directions for research. So what is a counterfactual? The way that I understand a counterfactual is a particular composition of interventions and conditioning. So here I have this very kind of abstract conceptual model, and I'm saying there is some state space which evolves over time. And so you can think of this as a kind of Gaussian process type thing. There's many possible different trajectories. We don't know which one will occur or had occurred. But then when we add some data, these red points here, we constrain the system. So this is our posterior belief now. So all of our trajectories have to pass through these points. And we can do this kind of using familiar Bayesian updating. And what a counterfactual is it takes a conditioned world, like the middle diagram, and it applies an intervention. And so I'm kind of symbolizing this with this dashed arrow here. So the key part is that we've cut the causal chains of history, and we've made a change at this particular point. And one of the interesting things is that now our data is in some sense invalidated, right? So none of the trajectories go through this particular red point. So counterfactuals have this particular structure, we condition and we apply interventions. To give you a kind of a more concrete example, so imagine we are observing two parties or two people, Alice and Bob, and they're playing a game. So Alice flips a coin, and we can model this with a Bernoulli distribution, heads or tails, true or false. Bob guesses the outcome, also model with a Bernoulli distribution. And then we're going to say if Bob guesses correctly, he's going to win $1. Otherwise, he'll win $0. And so now we can conduct a counterfactual. Given that Bob had guessed heads, and also given that he'd won, would he have won if he had guessed tails? And so intuitively, the answer is no, he would not have won because, given that he guessed heads and won, this implies that Alice threw heads. And if he had bet it differently, or if he had guessed differently, he would have lost. So this is the structure of the counterfactual. And this is the kind of thing that we're trying to automate. And so if you look to, the previous example is a kind of a familiar, literally a textbook example. And the point of this work is to extend this kind of reasoning to more complicated models. And so one of the examples we have in the paper is this kind of population model. I'm sure it's familiar to many of you, where you have a population of predators and a population of prey. And the kind of questions that we're asking are, okay, given that we've seen some amount of prey or some amount of predators, for instance, maybe the predators are going extinct, we can ask questions such as, if we had made an intervention in the past, could we have avoided this situation? Right? And these are clearly probabilistic questions because we don't know the full state of the system, even given our observations. And so one of the nice things is that we can ask these causal counterfactual questions in these simulation models. That's really the objective. But we can also ask things which are difficult to ask in the standard framework. For instance, we might say, given we intervened when the population of prey was at its highest, so the intervention we're doing is a function of the posterior. These are the kinds of questions that probabilistic programming languages allow us to ask if we equip them with kind of rich counterfactual tools. Another example is kind of a simple migration example. So here we have this idyllic grid world where we have a population of people, and these people have different desires and beliefs about the world, and they migrate over land or sea to areas where they want to be. And so we can do a kind of inverse reinforcement learning to figure out their beliefs and their desires given the migration patterns. But then we can ask counterfactual questions, such as, had there been a barrier around this region, would the migration have been different? Counterfactuals, like I said earlier, are often used in service of something else. So here's a very simple causal question. Did throwing the projectile at this angle cause it to hit the ball? And so what I'm showing you here is our system of essentially making modifications to ascertain that, yes, indeed, this particular direction in which we threw the projectile did cause it to hit the ball. A slightly more complex example in a similar vein is asking, it's kind of a occlusion problem. So if you focus on this image on the left first, asking, is this gray ball on the left-hand side the cause of our inability to see the yellow ball behind it? And so again, the system is making adjustments to figure out, actually, yes, it is the cause. Right, and so I guess I want to convey two things. One, yes, the answer is intuitive, it's maybe even obvious, but what we want is systems to automate this kind of reasoning. And this example is actually a little bit more complex, simultaneously doing this kind of causal counterfactual reasoning, but also we're doing this based on images. So we have to simultaneously look at these images, do a kind of inverse rendering to figure out our belief about the state of the world, and in these possible, hypothetical posterior worlds, answer the counterfactual question. And so again, what probabilistic programming allows us to do is combine these things in complicated and interesting ways. So what I want to go over now is how we've approached this in Omega, and the way that I'm going to frame it is in terms of what I think are the key problems that any system of counterfactuals, inference and probabilistic programs will have to solve. And so the first and the primary problem is what I call this redefinition problem. And that is that interventions, which are kind of at the core of counterfactuals, require that you redefine values after they've already been defined. And this is just incompatible with the way that most programming languages work. nothing, probabilistic or otherwise. And so what do I mean? So we have this very simple example, x equals 0, so y equals x plus 1, so clearly y is 1. And so I want to compute what would y have been had x been minus 1, right? And so intuitively the answer is 0. But the problem is that by the time I've got to here, y has already been defined. I don't have any reference to x. I can't just change x's parent in this way in a normal programming language. And so another way to understand this is that most programming languages have what's called an eager semantics. And kind of formally, this means that the environment, which is a kind of a mapping between, in eager semantics, is a mapping between variables and their values. And so you should think about this as like the thing that's going on in the background when you interpret this program. And so if we just go through line by line, I could say at the initial state, the environment is empty. And then after the first line, x gets assigned to 0. And after the second line, x gets assigned to 0 and y gets assigned to 1. And then finally, we evaluate the value of y just by looking it up in this mapping. So that's eager semantics. Is very intuitive. It's how most programming languages work. But the problem is it doesn't support the kinds of interventions that we want to do. So what lazy semantics allows us to do is say, is to be able to do these interventions, and I'll show you how. And this is a little bit intricate, so look in the paper for more details. But the high-level idea is we store instead this mapping gamma, which is a function from our environment x to this pair, which is an environment and the expression that defined it. So what do I mean by that? So again, we just go through this example. Originally, the environment is empty, and then after the first step, the environment is a mapping from to the value, the expression that defined it, which is just 0, and the environment in which it was defined, which was empty. It's more interesting in the next step where we see that y, x is the same as before, but y, it has this expression x plus 1, and the environment is the previous environment, right? So this is perhaps a little bit strange, but this is how lazy semantics works. And so what it means is that when we go to evaluate the value of y, we look up its expression, x plus 1, and the environment in which it was defined. And we do this, and we evaluate, and so we get the value 1. So that's how lazy semantics works. And what we do to implement the do operator, that do changes the environment. So previously, the environment was like this, x gets assigned to 0 and 0. And what do does is that it changes this value of x in this environment to be minus 1. And again, here to be minus 1. And so what that means is that when I evaluate this y in this new environment, I get the value that I expect, which is 0. So that is kind of how, this is kind of the core contribution of the paper. Again, it's a little bit intricate, but the high-level idea is that we need to change the language semantics to store how our expressions are defined in order to change them at some later point in time. The second problem that any kind of approach to counterfactual inference must solve is this problem of composition, right? And so counterfactuals have this particular structure, x given do some intervention given some observational data. But there's many different possible ways to compose these things together, right? And so some of these have names and some of them don't have any names. We just kind of explored them because we have this ability to compose them in different ways. And so how can we support that? The main kind of idea conceptually behind how Omega allows this composition is to treat both interventions and conditioning as high-order operators, which themselves produce random variables or produce variables. So if we go back to the slide, if x is a variable and y is a variable, then this thing, x bar y, is itself a first-class random variable. And this whole thing itself is a first-class random variable. And so this is a kind of a small but critical part of the puzzle because it allows us to compose these things in the important way, as long as the types match. And what I think is an interesting question is, what are the other interesting questions, causal questions, which haven't been so explored in the literature, but we can now express because we have a probabilistic programming language that allows us to compose them in kind of the intuitive and arbitrary ways. The third problem that I think any approach to counterfactual inference will have to solve in PPLs is variable dimensional models. And so here I have a very simple example. So I've got, this is pseudocode, this is not real Omega. But the point is that I have two populations of individuals, N and M, and so pop1 and pop2, and the number of people in these populations is determined by N and M. And so now I've got a sample, and I'm just visualizing these super emojis. And I can ask the question, had n been 5, what would the populations have been? And so what can happen if you're not careful is that if I change n to 5, all of these people who were previously in population 2 get transferred up to population 1, which is often not what we want and not what we expect. But this is, this will happen if you're not careful about how you assign the identities to variables in your probabilistic program. And so this is very similar to a problem in posterior inference discussed by Wingate and all. But the main conceptual difference here is that when you go to the causal inference world, it has kind of severe semantic consequences. And it's not just about efficiency or how fast or effective you can do inference. And so what we do is that we say, okay, the identity of a random variable is not just its kind of positioning dynamically, but it's a combination of its structural position in code as well as its dynamical runtime information. And we can talk offline about how we actually implement that. Kind of the final problem that we solve is distributed families. And if we take, again, a simple example, so suppose I have X as a normal distribution, and I want to ask the question, what would X have been, sorry, given that X is equals to 0.2, what would X have been had sigma been 2, right? And so the problem is that this is ambiguous. It depends on how X was generated from this normal distribution. And so at a high level, the problem is that it's ambiguous. And it's that we are taking these parameter families, this normal distribution family, to be primitives. And so what we do in Omega is that we simply don't do that. And we take primitive distributions to be parameterless. So we only have things like a standard normal or a standard uniform as our primitive distributions. And so this raises a kind of a hard conceptual question, which is that how do we condition? And so at a high level, what we do is that if I condition the output of our, I condition X, I have to do a kind of inversion to go back up and figure out what are the values of the underlying exogenous variables that cause it to take this value.
Zenna, my apology, just you have 1 minute left. Thank you.
Thank you. So I will skip over that slide. I'm just going to just show a few open problems. So one open problem is in natural language, the way that we think about counterfactuals is propositional. I would say, what if I had taken a different block from this Jenga tower? Would it have fallen over, right? But this is undefined in terms of counterfactual inference because it depends on precisely how I took that block. And so there's this tension between how do we describe counterfactual inference at a high level? How can I just write down this question to an inference procedure and get a good answer and not have to specify every particular detail versus how do we avoid these problems of ambiguity? So in terms of future work, one of the areas that we're going to is actual causality and explanation. So we're asking, did some event actually cause some other event B? And why did this event occur? So why did this bridge collapse? And this is what I think is really the kind of the core mission of counterfactual inference. And this is where we're going into the future. And so finally, I'd just like to conclude. So my main points are that programs are causal by the nature of how the program runs. Interventions require change in the dynamics. Counterfactuals are an important operator, but as I showed you earlier, there's many different things that we could ask. And there's many different causal questions that we could ask. And there's subtle questions like values and this kind of correspondence between the counterfactual and the hypothetical world that we need to determine. So thanks for your time. Feel free to check out this work. The preprint is online and the code is available to try out.
Thank you. That was very interesting. It's nice to have a talk with semantics and inference. Okay, so we have time for a question. It's an interesting technical question. Could you explain how this approach to interventions by way of lazy environment definitions relates to approaches in which trace-based evaluation is used to implement interventions?
Yeah, so so one of the So the way that trace-based evaluations is that you can modify the trace, and the trace stores a relationship between every random variable in your program and its value, right? And so I think there are some limitations to that approach. In particular, if you want to intervene on something which is not in your trace, you can't do it. And so one of the nice things about this kind of lazy evaluation approach is that you can intervene on any value which you have which is bound to a variable. And so at a more conceptual level, the way that we approach this in Omega is that there's a very clear delineation between the causal concepts and the probabilistic concepts, and they don't interact, but they can compose in interesting ways.
Yep. All right. Thank you very much. Thank you. So our next